You want to analyze a dataset, where and how to start the analysis? This is what we will answer in this video. You will be able to identify and explain patterns in data and hopefully produce a full exploratory data analysis report using Python and Jupyter notebooks. This is not all. You'll also learn the modules used in analytics along the way. This video is part of a series focused on analytics and machine learning in Python, where you will learn the concepts by doing actual projects. In case you have no coding background, don't worry, I got you covered. Check the link in the description box. In order to understand data analysis, there are several concepts that you need to be aware of. We are going to demonstrate these concepts using simple example now and then actual implementation using real data. Let's start by importing the modules that we will use in our analysis. NumPy is a module concerned with doing arithmetic and mathematical calculations fast in Python, and Pandas is a module that will enable us to deal with tabular data. Imagine that we have this specific set of numbers and we want to describe them or summarize them using a single statistic or value. One way to do it is to count this list, and this can be done by length of feet1. We can say that there are 5 items in this list. Another way is to calculate the average of the numbers or the values. And note that the average is the expected value of the number within the list. So I can predict or expect that the values are within the range of 50. To understand the spread of values around this expected value or the average, we use the variance. So what is variance? It is basically the spread of values around the average. So 800 is not that informative, and in order to understand variance in details, let's look at the calculation. It's basically the sum of squared deviation of a given value from its mean. Let's break down this equation. First, this is the deviation of a specific value from its mean, and let's square it. We can see this, for example, 10 minus 50, this is the expected value of the item in the list, is negative 40, 30 minus 50 is negative 20, and so on. And if we added these numbers together, the negative ones will cancel the positive ones. To avoid this, we use the squaring. Now we sum it and divide by the number of values inside this list. Still, this number is not elaborative enough of how each value actually deviates from its expected value. To find another meaningful value that expresses such deviation in terms of the units of these items, we use the standard deviation. So if we use NumPy, it's almost 29, and it's basically the square root of variance. So if we want to give a single value description of feet1, we can say that its expected value or mean to be 50 and the standard deviation to be 29. What if we have another range of values and we want to understand the relationship between these two ranges? First of all, is there any relationship between both? And what is the magnitude and direction of such relationship? In order to summarize this relationship, we calculate the covariance of these two ranges. Covariance is simply the degree of association between two random variables. If both grow in the same direction, the covariance is positive, and vice versa. Let's check this here. We can directly eyeball that as feet1 increase, feet2 also increase. It says here that the covariance is 100. Okay, still like the variance, what does 100 actually mean? To have a scaled measure of this covariance, we use correlation. There are many forms of correlation calculation. The most common one is Pearson correlation coefficient, which is basically the covariance divided by the standard deviation. We can use NumPy. the correlation coefficient is 1. Correlation coefficient ranges between -1 and 1. -1 means that the relationship is inversely proportionate, which means that one variable increase, the other decrease, and positive is the other way around. -1 and +1 is the maximum value of each correlation coefficient. So if we have -1, it's a perfectly negative relationship, and if it's 1, it's perfectly positive relationship. To better understand covariance and correlation coefficient, let's look at their calculation. Covariance is simply the dot product or the sum of the deviation of each value for each variable from its mean. So this is the deviation of each value in variable 1 multiply deviation in variable 2 . And let's sum this all together. Divided by n. We can see here that it's 80, but when we calculated using NumPy, it gave us 100. The reason of this difference is that we here divided by the total number of samples in the variable, but NumPy divides by n minus 1. Don't worry much about the n and n minus 1. If we here divide by n minus 1, it will give us the same result. So now we understand covariance and how it is calculated. What about the correlation coefficient? It's simply the covariance divided by the standard deviation. Let's name this covariance, and to calculate the correlation coefficient, it will be covariance divided by product of standard deviation for each variable. We can see that it's 1 point, it actually cannot exceed 1. This is because we are here using n minus 1 and the standard deviation is calculated using n. We have to account for this using delta degree of freedom. When we are calculating any statistic using sample data, we want to account for the fact that this is a sample and there is some sort of bias. The n and n minus 1 just to differentiate sample from population. So correlation coefficient we just calculated is exactly the same as NumPy. To summarize what we've learned so far, we now understand what's variance, what's standard deviation, and how to measure the relationship between two numeric variables using covariance and coefficient of correlation. One last thing that we need to be aware of is the effect of outliers on all these calculations. So for example, feet, it will be same of feet 1. Instead of 90, we will make it 900. So we can say here that the range, these last two numbers, is completely different and wider than any of these numbers. This number is considered to be an outlier, and outlier doesn't follow the norm of the rest of the numbers or the rest of the pack. This will affect the calculation of all statistics. We can see here the mean is much larger than the same list without the outlier. Same if you calculated the variance. See the difference, this huge difference between both. And also we can see that variance in general is always have a significant magnitude because of the squaring factor that we've discussed earlier. That's why standard deviation is much more useful in interpreting the dispersion within the values using the same unit of measurement of these values. So for example, if all feet 1 represented dollar values, for example, so we can say that there is a variance of $800 because it's not the case, it's a square dollar. But when we calculate the standard deviation, we can say that the deviation is of X dollar. One way to control the effect of outlier is to use log transformation, and log transformation basically decreases the scale of the values to a given base. For example, log 1p is just add 1 to each value before it starts the log transformation. This is basically because if you have 0 in the range, it adds 1 to avoid 0 division. We can see that the scale significantly decreased to these new values, but preserving the magnitude of the 900 to be the highest value also after log transformation, but the distance between each values is much more smaller than earlier. One benefit of this is when we want to visualize these two features, for example, using a non-log transformed values. The outlier is considerably distant from the other data points, and they are almost on a same straight line. Rather, if we used log transformed values, we can see here that the scale is much more smaller and the difference between all the points is much more visible than earlier. So to summarize what we have learned so far, we now able to describe variables using single values such as count, mean, variance, and standard deviation. We are able to assess the degree of association between two random variables using covariance and correlation, and we know what outliers are and how to deal with them. It's time to start an actual analysis using real data. The dataset that we'll be using today is insurance dataset, and in order to add a dataset to your notebook, we go to this button, File, and Upload. So we now have the dataset uploaded to the notebook. We simply copy path and read the file using pandas. So we'll name the dataset using a variable called df. df stands for data frame equal pd.read csv and pass in the path for the file. Let's look at the dataset now. So let's understand this dataset better. I'll leave a link for this dataset in the description box. This data is for customers of an insurance company, and it includes demographic description or feature of each customer, such as age, gender, BMI, how many children, does he smoke or not, the region, and charges. Charges here is the amount of insurance expense that each customer has incurred during the period of assessment. And the aim of this dataset is to be able to predict and understand what does actually impact the insurance cost for each customer and how to profile each customer in a separate risk profile for a calculation of the amount of insurance premium it charges to each customer. So we basically want to understand for each customer what does influence the amount of insurance charge that is incurred by that customer. One nice feature of Colab is that we can turn this table into an interactive table using this magic wand here. We can now sort the data by, for example, age, by charges. We can change the amount displayed per each page. We can jump between the data and a lot of different stuff. But since we also want to learn how to use pandas module, we are not going to rely on this interactive table much. So let's delete this table and run it again. The theme for this analysis will be as follows. We'll first understand the different types of data and how to deal with each data type separately using numeric analysis and visualization. We can observe that there are two types of data here. There are numeric data and there are categorical data. For example, age is a numeric data and gender is a categorical data, and each of them has its own type of analysis that can be done. We'll first begin with univariate analysis, and univariate analysis is similar to what we said in the introduction. It's just description of what's actually going on in this data. So we start with dataframe.info, And info method summarizes the data frame as follows. The number of entries or samples or observations there are, or customers in the data set, how many columns, whether there are empty cells in each column, and the data type of each column. So for example, age is int, which means it's number, gender is object, which means it's categorical or string, and so on. This is actually important because sometimes data is read in incorrect way. So you can say that, for example, gender is int, and you need to handle this before going on further with your analysis. Another thing to glance at is null values. We are gonna calculate how many empty cells are there. We already know that there is no empty cells because all cells here is non-null, but it's also important to know how to do it in case of there has been any non-cell or we noted any non-cells. So df dot is null, and is null will display all cells that are that have empty values, and we can see here that for each column it displays false. So this means that there's no empty cells here, so on and so forth for each of the values. Of course, it's tourniqueted view. We don't see all the records. As you can see, there are almost 1K record, which it can be displayed at once. So we can sum the null values to get a summary of all values in each column. And here we can see that for each column it summed the null values, and as we know there is no null values, so it's all displayed as 0. Next, let's look at the categorical features, and for each categorical feature we are interested in knowing how many levels are there within each category. For example, we say df.nUnique, and nUnique is the number of unique values within each column. And we can see here for each column it printed the number of unique values. For example, age we have 47 unique values, gender we have 2, male or female, BMI 548, so on and so forth. Finally, in order to see the first 5 records of the dataset, we use df.head. Similarly, if we want to see the last 5 records, we use tail. And by this we have quick overview of the dataset in general, and we can know how to move forward. In order to gather all this analysis we have done so far into a single line of code, we can use display and just include all the codes we've used. So df.info, df.isNull, df.nUnique, and lastly df.head. Here we can see all the methods we've used printed below each other. The reason we use display instead of print because we want to preserve the tabular form of the head. For example, if we used print, you can see it displayed or printed the table in such way. So to summarize the dataset so far, we have 7 columns, none null values, or there is no missing values. Data types are correctly specified, and we have only 1 duplicated record because we can see that charges, the number of unique items is 1337, and we have a total of 1338. So this means that there is 1 duplicated record in the dataset. Let's start by doing a univariate analysis, and this will be mainly calculating different statistics for numeric and categorical variables. A simple and straightforward method to do univariate statistics using pandas is the describe method. So we say df.describe, and in describe, if we run the cell as is, it only picks the numeric variables only, but if we want to include categorical variables as well, we use include equal all. So we can see that it included both numeric columns and categorical columns. Now let's transpose this so we have a better view of what's going on. The describe function calculated several statistics that we have already discussed before. Count, for example, standard deviation, mean, min, max, and the quartiles for each numeric values. Note that not each statistic is calculated for both values. For example, categorical values, we have only the count, unique, top, and frequency. So, for example, we see here that the total male customers is 676. It's almost half. So we can say that it is a somewhat balanced data set. For age, we can see that the numbers are somewhat uniformly distributed. We see that the average is 40, the 75th percentile is 51. Let's discuss what is the 25th, 50, and the 57th percentile. 25th means that 25% of the data lies below 27, the age of 27. 27 does not mean that it's necessarily a number or a value inside the variable. Rather, it's just a threshold below which 25% of the data lies. 50 is similarly, 50% of the data lies below 39, the age of 39, and 50 is the median. The median is the middle value of the data. And actually, we can know the characteristics of distribution of values by just these numbers. For example, if we look at charges, we'll see that the mean, which is 13K, is higher than the median, being 9K, and this is actually one of the characteristics of a positively skewed distribution. And we will talk about distribution and what is positive, what is negative skew, and so on. But we can note the characteristic of a distribution just by analyzing and looking at these figures. We can also note that there are some outliers because the 75th percentile lies below 16K, and the maximum amount of charges in this dataset is 63K. So there are some values that will be considered as outlier, and actually this justifies why do we have a positive skew. One last thing is that most of customers are non-smokers. Now let's try to understand quantiles better. If I want to display a specific column in pandas, I have several options. First, I can say df.charges. Run the cell. It displays the column in the form of a series. I can wrap the column between two square brackets, and it displays also the column but in the form of a table. I can display several columns using the same approach. For example, lastly, I can use drop feature and drop all the columns that I don't want it to be displayed. So for example, we're gonna drop all the columns except charges, so age, gender, and so on. Yeah, because we haven't specified the axis. We either can use this form instead of using square bracket. We can specify that these are the columns equal, and it displays all the columns except those that are dropped. Or we can use the same approach without specifying column and select the axis to be 1. 1 means column, 0 means rows. If you said here the axis is 0, it will give an error because there is no row named age, gender, BMI, and so on. That will give you an error that age, BMI, gender, and children are not found in axis, which basically means that there is no axis called this stuff in the rows. This is how to display specific columns or to filter the data frame. And now let's get back to our example of understanding quantiles. So if we look at charges and we sort the values, 25th quantile means that 25% of the data lies below 4,700. It might not be visible because of this ternication. So we used the magic wand to display the table in an interactive fashion. Now if we sort by charges, 25% of the data lies below 4K. So as you can see here, when the data is sorted, we expect that 25% of the data is below 4K. So we go 10, 11, yeah. Up to this point, this represents 25% of the data, and in order to make sure, we can filter the data frame by the quantile. If you want to filter a data frame by a specific number or specific range, we first start by the data frame itself and use square bracket, then specify the condition that you want the filter to be executed. In our case, we want to filter by the first quantile, so df.charges smaller than df.charges.quantile 0.25. Now we're basically sorting or filtering the data frame by using the charges values that are below 25% or at the first quantile. We see here that it's 335 rows. We can calculate the percentage of this observation to the total number of observation in the data frame to make sure that these represent actually 25% of the data. So if we say .shape, shapes gives us the number of rows and columns. So if we select 0, these are the observations that lie in the first quartile of charges, and divided by total number of observation in the data set, which is df.shape, also 0, it gives us 25%. So we understand now what does 25% equal 4.7K means. It means that 25% of the data lies below 4.7K in terms of charges. So what can we do with quantiles? One thing we can do is to calculate the interquartile range. It's basically Q3 minus Q1. For example, charges, df.charges.quantile 0.75. This is the third quantile, minus the first quartile, gives us this number. So this is the IQR, interquartile range. We can use this figure to identify outliers. For example, any point that extends beyond interquartile range multiplied by 1.5 is considered an outlier. And if we wanna visualize this, we can use box plot. So we visualized the charges column using a box plot, and box plot simply conveys the calculation we've just did here. This box here represents the middle 50% of the data. The lowest point is the first quartile, this one that extends here, and this edge of the box is the third quartile. The distance between them is the IQR. The middle line is the median, and we can note that it is positively skewed distribution because data is much more spread towards the right side of the median line. In order to understand whiskers better, let's understand how it's calculated. We have already calculated the interquartile range, and we multiplied by 1.5, which is the maximum that should be extended to. Now, if we add Q3 to this equation, for example, it's 16.6K, we get about 34K. And we can actually see here that the whisker ends at almost 34K, and any point extends beyond that is considered to be an outlier. So whiskers extend to a maximum of 1.5 interquartile range plus the Q3 or Q2 values. The extension of the whisker should accommodate the max and min points, but we can see here that the maximum point is 63K, which is way higher than 34K, so thus it's considered to be an outlier. If the maximum point was within 34K, we wouldn't have seen these outlier points. One final thing to note is that it's not necessary that whiskers extend to 1.5 into IQR. If the max and min points are less than 1.5 IQR, the whisker extends to the max and min points, then stops. Now, if we want to visualize these statistics instead of running the describe function, we can do this just easily. We'll start by first separating the categorical from numeric columns by using a select method. And the object here refers to all the columns being referenced as a string. Object means string in pandas. Dot columns. And let's look at cat columns. It captures the gender, smoker, and region features. So if we want to identify the numeric column, we will just select all the columns that are not included in the cat column. So if we call df.columns separately, it displays all the columns. Okay, so this is a list. And if we want to make a selection from this list, we can do this by using Boolean indexing. So df.columns display all the column inside the data frame, and if we want to make a Boolean index, we can simply say df.columns dot is in cat columns, and is in displays all the columns inside the cat column. So if we call the data frame and then select all the columns that is inside the cat columns, it will only display the categorical columns. It displayed gender, smoker, region, and so on. These are the cat columns. If I want to make a Boolean index which evaluates to false, it's as if I'm saying select all the columns except these columns. I use tilde. It grabs the numeric columns only. Now if I look at the numeric columns, I have all the numeric columns separated, and similarly cat columns. Let's visualize univariate visualizations for numeric columns, and this will be basically histogram. So we'll use Seaborn histplot, and we will specify the color. A histogram simply bins all the values inside a given column and display its frequency. So for example, from 0 to 10k we have like 4 to 5 bins, and each bin has a different range of values. Most of the values are concentrated in the lower range, and we have only smaller amount of values above 60k insurance charges. Regarding the shape of the histogram, we can see that it is positively skewed. It means that it has a tail that is going towards the positive values. It means that these values are not normally distributed, and we don't have an equal representation of each value within this given value. So if we are to predict charges, for example, we don't have enough samples from each value to make an accurate prediction. Of course, our prediction at the lower end of the values will be much more accurate than those of the higher end, because we simply don't have enough data to cover them. We can add a kernel density estimator. It plots a curve as a smoother for the histogram, so we can see that instead of having a dips like here, it just smooths out dips in the histogram and links all the values in a nicely plotted curve. If we wanna display histograms for all the numeric variables, we can simply do a for loop. We are gonna loop over each column inside the numeric column and plot a histogram, and this code snippet here establishes how many figures that we need to have inside each row. We want to have a maximum of 4 figures inside a given row. So in order to do this, we here have to specify the number of rows and the number of columns, and we calculate the number of columns automatically. Enumerate creates an index and a range for each value within the numeric column. So we will iterate over all the columns inside the numeric column and create the subplot figure in figure we have instantiated above. We basically say for each column inside numeric columns, just add a figure, and this figure is going to be a hist plot, and we here call the column to be plotted using df c, and C stands for the column inside the numeric column, and plot tightly out makes each plotted figure at an equal spacing, and we will also rotate the X tick marks so it can be visible easily. Run this code, and we see here each column inside the numeric columns of the dataset plotted on equally spaced figure. Age is uniformly distributed, which means that it's equally distributed among the dataset, except for those within the 20 years old. We can see also a dip at almost 38, 39 years old. BMI is normally distributed, and normal distribution is this nice bell-shaped curve distribution. So why do we even bother by looking at the histogram? For two things mainly. First, to understand the distribution of the values within each variable, and also to note where might be problematic variables that can cause some problems later when we do machine learning exercise or predictive exercise. But let's not worry about this for now. Just understand what are histograms and that they are a graphical depictions of the numeric statistics that we saw earlier. We can understand different component of values within each variable just by looking at its histogram. For example, a BMI is normally distributed, so we can expect that around 68% of values are within one standard deviation from the mean, 95% of values are within two standard deviations from the mean, and 99.7% of values are within three standard deviations from the mean. What do these numbers actually do and tell us? It means that if we know the mean for a specific normal distribution, we can make a guess of other values within that distribution. This is known as the empirical rule. Let's try to understand distributions better. To do this, we are going to discuss the normal distribution. This bell-shaped curve depicts a normal distribution, and it means that several things actually. First, the mean, median, and mode are all equal. So we'd expect that the mean will be 30, the median will be 30, mode will be 30, and so on. When we discussed the empirical rule, we said that around 68% of values are within one standard deviation, and so on, which means that the spread of the data around this mean is to be expressed by 1, 2, and 3 units of standard deviation, as we mentioned earlier. We can directly see this on this plotted histogram because of the scale, and to demonstrate this, we are going to use the standard normal distribution. Standard normal distribution is a normal distribution that has a zero mean and a unit, which means one standard deviation. To transform this scale of BMI from being in this numeric scale to its standard normal values, which is referred to as also z-score. One way to do it is to subtract the mean from each value in the designated column and divide by the standard deviation. This is called standardization. And what are these numbers actually do? It's just representing the numeric values that were before in terms of their deviation from the mean. So let's check what was the first data point. So the first data point is 27 or almost 28. Instead of saying 28, we say it's negative 0.45 from the mean. And if we consider the mean to be 30, so 27 would be in this area, so it's negative because it's to the left side of the mean, and it's within one standard deviation from the mean. Now we can actually plot this instead of the original plot, and now we can see here that the scale changed from being this scale 30, 35, 25 to being 0, 1, 2, and 3. We can see here that the mean is centered at 0, and we know that the mean is 30, so instead of saying the mean is 30, we say 0 mean. This is what the empirical rules mean. its data points are spread around the mean within 1 and 2, 3 standard deviation. So we here have the mean of 30 and it's described by the z-score of 0. So 27, for example, would be here. That's why it was denoted by -45. 33 would be positive. It would be in this portion here, and so on. So we now understand what is the empirical rule and the standard normal distribution, or aka Z distribution, and how to transform your data to a Z distributed data. Instead of calculating z-scores manually, we can use libraries for this. For example, sklearn. sklearn is a dedicated library for machine learning, and it includes several methods that we can use to clean, pre-process, and build models using Python. So let's import our scaler from sklearn. There are actually many different scalars, but for this demonstration, we're going to use the standard scaler, and we are going to pass our column. So here there are two processes that is being done. First, fitting, where the calculations are being made, and transformation, where data is actually changed from the original numeric values to these scores values. We can actually call fit alone, then transform in another call, but at this time we are gonna call fit and transform at one go. We can see that it transformed the values into their z-score. We can go ahead and plot these values. We get the exact same output as we did earlier. Now, if we want to visualize the categorical columns, we'll also use for loop to do the same as we did with histograms, but this time we are going to use count plots. Count plots displays each category and the relative count of each level within each category. And two things are changed here. First, we used paired coloring palette, and we ordered the bars sequentially. So let's understand what does this code snippet do. If we say df.gender, for example, .valueCount.sort in index, we see that it captured female and male. And in order to understand this, let's first decompose this code. So value counts summarizes the categories and their relative frequency. Then when we sort values, it sorts from smallest to highest. And if you want to capture only the name of the categories and not the values, we use .index. And this is what's actually passed here for the ordering parameter of the count plot. So we can see here that, as we said, it's equally distributed in terms of gender. There are much more non-smokers than smokers, and also customers are equally distributed among regions, except for Southeast, which has a relative larger amount of customers than other regions. To wrap this portion of univariate statistics, we started by describe, and in describe we were able to understand each feature, the demographic of each customers, and we were also able to visualize these features to confirm our understanding and obtain better summarization of the univariate statistics. Now into bivariate analysis. By bivariate, we are going to look into relationships between each variable. We are actually concerned with understanding the relationship between all the variables and the charge variable, and let's call the charge our target variable. It is the one we want to analyze and understand what affects the amount of a charge for each customer. So let's begin with understanding the relationship between numeric and numeric variables. To do this, we are going to use correlation. Correlation actually is easy to implement using pandas. We simply say df.cor. It displays the correlation among each variable and itself, and also the other variables. Since we are only interested in a charge variable against each other variable, we can see that age is 0.29, and we already understand that 0.29, 0.19, and 0.6 is a measure of strength of association between each two variables. We can see here that age is the highly associated variable with charges, followed by BMI and children. All variables are positively associated with charges. Instead of having correlation as is, we can visualize a correlation heat map using sense heat map. So sense.heatmap df correlation. Here we can see the heat map is plotted each variable against each other. The color bar here displays the strength of the correlation. So 1 means perfect positive correlation and the negative 1 means negative correlation. As the color tends to be lighter, this means that the correlation strength tends to be more significant. So for example, we know from earlier that age was the most significant or the most highly correlated feature with charge. It has a lighter color than BMI and children. Instead of just relying on colors, we can display the strength as a text inside each square. We can here see how much each variable is correlated with one another. We can also decrease the decimal display by using format, so FMT equal 0.2F, for example, for 2 decimal point only, and it displays here 30, 27, and so on. What's important to know about correlation in general is that it does not imply causation. So it doesn't mean that because age is highly correlated with charge, older customers will have higher charge than younger ones. So just keep in mind that correlation is just an indication of the association between two variables, but it does not mean that one variable actually causes or forces a change in another one. Another way to visualize a bivariate relationship between numeric and numeric columns is using scatter plots. We will use joint plots, and joint plots is a nice way to display scatter plot along with histograms. In this code, we just loop over in numeric columns and exclude the charges because we want to plot other variables against charges. And we call the joint plot use x-axis being the variable we are interested in and the y-axis is charges. Run this code. Joint plots display the scatter plot where the variable is on the x-axis and charges on the y-axis, as well as the histogram. We can observe from this scatter plot is that there are 3 distinct groups of customers. Those that are denoted by these data points, and this middle portion, and lastly the upper portion. So one thing to investigate is why there are 3 distinct groups. When we look at BMI, for example, we can see also that there are 2 distinct groups, those having a smaller charge values and those having a higher charge one. Apart from others that are scattered around, we can also note that for customers with age 50, 2 that have small charge value and others that have a relatively higher charge value, we can look into these specific 3 customers and understand why such difference exists. Finally, if we look at children, as we said, it's discrete and it's not actually a perfect way to visualize a discrete value using scatter plot like this, so we can add trend lines. What are trend lines? First of all, let's include trend lines. Reg here stands for regression. And what does this actually do? It includes a regression fit, and we'll talk about regression separately in another course, but just note that this line represents that of best fit. Regression is basically a statistical technique that relates a dependent variable, and here the dependent variable is charges, to an independent one being age, and captures the relationship between those 2 variables in a specific equation, and this line represents this equation. So if we are to make prediction, we use regression, and our regression line or the line of best fit will fall in this area. What does this line really represent? It represents that as age increase, charges tends to increase also by specific amounts. Of course, these specific amounts or the formula is not displayed on the graph, and we don't have a way to access the formula using the joint plot because the creators of joint plots or Seaborn in general didn't make this accessible, but we have other ways to calculate this form of relationship. We said that correlation doesn't imply causation, and do not expect that highly correlated variables mean that change in one variable has a significant impact on the other. But regression tends to explain this relationship. So if correlation indicates the strength of the relationship, regression explains such relationship and depicts it in a more quantifiable and formulated way. So similarly for BMI, we see that here as a BMI increase, we also tend to see an increase in charge. The shaded area around the line represent possibilities where the line can be fitted. So the line can be shifted upwards a bit or can be shifted downwards a bit. Of course, we are fitting a regression using a single variable, and as we add more variables to the equation, the line tends to change, and of course the formula of that line tends to change. Finally, if we come to look at children, we can see also an upward trend. As number of children increase, charges tend to increase, but slightly less than the other two variables. So to summarize what we have observed from the scatter plot and the trend lines, we have seen that there are three distinct groups when we plotted using age and charges, and we also noted that the line tends to be pulled downwards towards the bottom of the plot rather than the middle or the upper section of the plot. And for BMI, we noted also two distinct groups and difference in the number of or the amount of charges for customers having the same age. So all these things need to be further investigated to better understand our data and identify patterns. So let's start with investigating the three distinct groups we saw in age group. So, okay, we see that below 10 there is a specific group, and up to 30 there is another, and above 30 the third one. So to make a filter on a data frame, we use the following method. We say df, then df dot charges equal or below 10,000. Okay, let's see this. It displays all the records below 10,000, but we want to obtain the summary statistics, so we say describe and include all, because we want to see numeric plus categorical feature. Let's transpose, and we just transpose to have a smaller table rather than the one we saw earlier. Okay, what we can see here is that this group is 100% non-smokers, because the frequency is 712 and the count is 712, so this means that 100% of this portion that is below 10K are non-smokers. Let's check the other groups, and this time we are going to use display. If you want to filter on two conditions, we use and. Let's write the other condition. It was below 30. Now we need to wrap each condition in a separate bracket. So for this second filter, show me all records of customers above 10K charges and below 30K charges. And we're also gonna use the describe and the transpose method. Close the display, run. Usually display displays the tables with spacing. I don't know why here in Colab it displays right below each other, but not a big deal. We can see here that smokers tend to be less than what we have seen earlier. The above, below 10K, they were 100% non-smoker, and here we can see that it's almost 27% smokers. If we subtract the smokers from the non-smokers, it will give us the amount of smokers, which is 122. So 122 divided by 464, it's around 27. 25% smokers. As smokers tend to get into the mix of customers, charges tends to increase. Let's see the last filter, which are customers above 30k charges. Okay, we have to close the filter. There is no comma. Okay, first there was no comma and I added a closed bracket by mistake. So let's see the last portion of customers. We already know that smokers is actually causing this, so let's look directly at the smoker composition. We see here that the top frequency of customers are smokers, almost 90, this is 90% or 49%. Almost 49% of this portion of customers are smokers, so this is actually what is causing the increase in charge. And we can see here the range or the distribution of charges among these customers. If we look back at our plot here, we can say that this portion, this lower portion, are all customers that are non-smoker, and this middle portion are customers of which some are smokers and some are not, and the above customers or the above portion of the plot are almost all smokers. So we can see that smoking tends to affect the charge value significantly. Now let's do the same for BMI. It's also contributed to smokers or smoking. So to summarize this, what we have learned so far about the data is that smoker customers tend to have higher insurance cost than other non-smoker customers, and that other variables does tend not to affect charges significantly. As we can see here that age group and gender, BMI, number of children, region are almost the same between these three customers, but what stands out in this customer is the fact that he is actually a smoker, and this is directly reflected in the amount of a charge he costed in that period. If we look at bivariate analysis between categorical and categorical feature, we can use crosstabs. Crosstabs simply summarizes the relationship between two categorical features into a summary table. To do crosstabs, we use pd.crosstab and pass the variables we wanna analyze. It will be df.smoker and region, for example. Let's look at the result. Okay, first off, let's normalize this table in order to see the percentage rather than absolute figures. We used normalize by index by smoker, so we can see the distribution of each type of smoker within the regions. Note that the rows adds to 100%, but columns does not add to 100%. We can also show the totals. We used round so that numbers actually look nicer, and let's understand what's actually happening in this table. We can see this distribution of smoker group across regions, and almost it's equal among all regions for non-smokers, and also similarly for the smoker group, but for the Southeast region, where smokers tend to be concentrated more than any other region. And we said earlier that rows adds to 100% and columns doesn't add to 100%. So this 27% means that in Southeast region occupies 27% of the data, Northwest Asian region 24%, and so on. And for the rows, as we said, Southeast region has the most concentration of the smoker group. Let's look at another cross tab using also smokers, but let's change the other categorical feature being gender. Here we can see that most smokers are male, and the males occupy 51% of the data, and females occupy 49% of the data. So there is no much differentiation between females and males, but we can say that there tends to be more smoker males than females. Lastly, let's look at gender in terms of region. There's actually no difference between regions in terms of male and female. We can see here that males tend to be slightly higher in Southeast region, and we know that Southeast region tend to have a slightly higher smoker group than other regions, and we know that smokers tend to be slightly higher in males, so it all makes sense that Southeast region has higher males that are actually smokers. So this is one way to understand the relationship between a categorical feature and a categorical feature. Now let's look at how to analyze categorical and numeric features. We know that categorical features by itself does not have a numeric value to analyze, but we can associate it with the target variable or the dependent variable that we are interested in and observe how does the mean of this variable changes by the change in each category. To do this, we can observe several plots, among which are histograms or KDA plots by each category. So this is basically the same loop that we did earlier. Instead of using hist plots, we use KDA plots, and we will know why in a second. We plot the charges or the dependent variable that we are interested in, and hue differentiates it by using the categories. And since we are looping inside the categories, we will plot charges given each category. KDA plots are almost exactly the same as histograms, but instead of displaying bars, it displays these nice smooth curves. We can see here that the hue part of the plot differentiates each plot by the given category. So for example, charges here is differentiated by gender, here it's differentiated by smoker group, and the last one differentiated by region. We can immediately observe that for gender and region, the curves tend to be plotted over each other with no separation. Unlike smoker group, here we can see a clear separation between the two histograms. This means that this group tend to have a different distribution than the other group. So when one group tends to have a different distribution of numbers than the other group, it means that it is significant in understanding the relationship for such dependent variables. And we already know that smoker group, as we seen earlier, tends to have different value in charges than other groups. Another way to visualize categorical features against numeric feature is to use violin plot. We will see violin plot in a few, but just to understand what is happening in this code, this is our normal loop. We have discussed it earlier. We just loop over the categorical features and plot a designated plot. And here we are ordering ascendingly using each group. In order to understand this code, let's look at it here. So df the group by gender, so it calculates the mean of each group within the gender variable. Then we sort by values. So we have the lowest mean first, followed by the highest, and we capture the index either being male or female. So this simply gives us female or male, and this will be the order in our violin plot. And this plot here, point plot, it just plots the mean of each group. So we just plot the group and the dependent variable. We keep the order as we discussed earlier, the color. Error bars, we don't need error bars, and error bars just depicts the confidence interval of the calculated mean, which we don't need this here. And line style just depicts the style of the line to be plotted. Let's look at the plot. Let's look at the plot without the point plots or the lines. These are violin plots, and actually violin plots are a nice way to visualize a distribution for a given numeric value categorized by a specific category. For example, we have seen from earlier here in the KDA plot that charges is not affected by the age or the gender category, and here we can see this happening also. If you remember from earlier that charges is positively skewed, so most of the values are within this region, 10K region. This is actually a positive skewed distribution, and if you look at this violin, this specific violin. For example, you see that this big ball here depicts the distribution of values in this area. So we have most of the values are concentrated here. So think of this as the positively skewed histogram you saw earlier for charges, but in terms of gender category. And these dotted lines represent the quartiles. This smaller line is the first quartile, and this is the third quartile. This is the 25th, and this is the 75th quartiles. And this here is the 50th, or the median of the range. The distance between these two dashed lines is the IQR, or interquartile range. And if we extend from the third quartile to 1.5 times IQR, similarly, if we extend from the first quartile 1.5 times IQR, we can start plotting the outliers. So you can look at this violin as all-in-one plot. The distribution of the values of charges, the ranges of the percentiles or the quartiles, and also the amount of outliers found within each category. We can see here for gender and for region, the distribution of values tend to follow that of charges, and it also tends to be more concentrated on the lower end and very small charges at the higher end. But when it comes to smoker, we can see there is a shift or change in the distribution of values. This means that a smoker group does affect the charges value as it affects the distribution of values within the charges variable. Now, if we look at the mean of each category, we are interested actually when we plot a categorical versus numeric, we are interested in the change in the mean of each category. We can see here that there is a slight change in the mean of the two variables when categorized by gender, also similarly to region, but we can see here a smaller uptick in the southeast region than other regions, but we can see a considerable and significant change when differentiated by smoker group. And this corroborates to what we have noted earlier here in the KDA plot. We can see here there is a significant differentiation between the two values of charges given each category. And this is also what is reflected here. We're gonna do a multivariate analysis, and this basically includes 3 or more variables within a single analysis, unlike the bivariate analysis where we looked at the relationship between 2 variables only. Let's understand this code and know what's actually going on. We are gonna look at the relationship between 2 numeric variables, but also categorize it by a single categorical variable. To do this, we are gonna use LM-plot. LM-plot is similar to joint plots. It plots a scatter plot, but enables us to have multiple regression lines plotted and also categorize the plot by a given categorical feature. So in our code here, we are looping over all numeric variables and plotting the numeric variables, the independent variable, against the dependent variable being the charges, the insurance charges, and categorizing the plot with a smoker feature. Here you can see that we did not include df.column or df.charges as a x and y and include it in a separate parameter called data, because this is how the LM plot reads our data. We are also gonna specify a specific color palette for each group, and here we are also specifying the color of the lines. But you can also note that after specifying colors for line, we did again specify colors for each line. This area here, ax.getLines 0 and ax.getLines 1, captures the first and second line in our plot and give it a different color. Why we did this? Because as you saw that lines has a shaded area and we want to differentiate the color of each line from the shaded area. So the shaded area will be in purple and the colors of the lines will be orchid and maroon. We can see here that these are similar to what we've seen earlier, the scatter plot, but it is categorized by each categorical variable that we specified. For example, if you recall, we said that there are 3 distinct groups when we looked at the age and the charge scatter plot, and we said that the lowest group of charges is non-smokers, the middle group has a mix between smokers and non-smoker, and the highest charges relate also to only smoker customers. The lines here represents two different regression lines, and this indicates basically that it is better to separate the data set here in order to model it into two separate data sets using the smoker group as a separation factor, because you see that the trend line of the non-smoker group does not capture most of the observation of the smokers one, similar to non-smoker group. If we look at the BMI scatter plot against charge categorized by smoker, we can see here this group of customers have higher insurance charges than those of the similar BMI range because of being smokers. And here we can see also an interesting pattern of customers who have almost similar insurance charge being smokers to those non-smokers given the same range of BMI. It would be interesting to close in these customers and identify what differentiates these customers, or what are the characteristics of these customers, and why being smoker and non-smoker does not affect or does not differentiate these customers from each other as the two other groups we saw earlier. We can also change the categorical feature to include another one. Let's, for example, try region. You can see that unlike smoker group, region tend to be randomly scattered, and also we can see here from the regression line that each region, each category of the region does not actually express or differ significantly from the other one in explaining the variation in charges. Lastly, we can visualize all categorical features inside this dataset using catplot. In order to understand what's going on here, we have the ordering that we discussed earlier. We are grouping by region, and we are using the mean of charges to sort values across the region. Then we are calling catplot using X as the region and Y is charges, categorizing by all the categorical features: smoker, gender, children. And let's look at the plot. This is actually called facet grid or faceting, where we plot all the features together. So for this section, the upper section, we have the female portion of customers, and the lower section is the male portion, and each block represents a number of children within each region. So for example, in this block here, we have females compared to male having 0 children across different regions, being either smoker or non-smoker. Smokers are in heavy purple. The spread of charges along the smoker group or non-smoker group is similar across different categorical features, except that smokers tend to have higher insurance charges than other non-smoker, and this has already been explored and discussed several times earlier. What I might be interested to know further is that why this female customer here has higher insurance charge than the rest of the other regions. So we know that all these are females, and what differentiates between them is the number of children. If we look, for example, here at 3 children, those with having 3 children, we can see that it's at par with those of smokers in other regions having less children. Let's look at these specific customers and try to understand them. Note that we here specified some columns to drop in order to lessen the amount of columns that we need to inspect. For example, if we remove this and display the DF as is, we see that there are several columns that we might not be interested in knowing, because we already have specified that children and smoker and gender type here in this filter. So drop these columns and transpose the dataset. Let's compare this subset to other subsets, and we start to note here some interesting patterns. For example, note this customer here, the 3781. All these customers are females, non-smokers, but different in the number of children. So we have this here customer as the age of 64 and has a 16K charge value. But if we look at this similar customer here, it's 64, almost similar BMI, and has also 16K. So there is almost no difference between the amount of charges between such customers, given that these have different amount of children. So we can say maybe it's the children that's causing, or maybe that children does not cause differentiation between these two customer charges. But if we look at another example, this customer here and this customer over there, they're in the same age group, have a different BMI, slightly higher BMI, actually higher BMI, but a significantly different charge value. This is 19K and this is 33K. So we can have a closer look at these different type of customers using another filter. And note here that we have selected some indexes to display. iLocation stands for index location, and in order to display a data frame directly using indexes, we use double square brackets and we specify the indexes that we want to look at. And here drop column is also to minimize the amount of columns that we have to look at. And lastly, we sort by different values. And note that we can actually sort by different columns, not only one column. So we first sort by charges, then age and BMI. Sorting starts sequentially. It first sorts by charges, then sorts by age and BMI. Here we can start to note the patterns that we have seen earlier. For example, this customer and this customer. These customers are also interesting because you can see here that it's almost in the same range of the amount of charges. This indicates that there might be other factors not included in this dataset that contributes to that variation in charges. Lastly, if we want to highlight some of these rows for better visualization, we can use styling and format. To continue your code, but on different line, we use the backslash. For styling, we use style.format, and we include which column that we wanna format. In our example here, we want to display numbers using commas and with 0 decimals. We are gonna use charges and BMI. Lastly, we apply a coloring formula and select the indexes that we want to color. So lambda x, and lambda is a one-off function. We will use our color to be purple if x.name, and x here is the row, if x.name is in these indexes. And now let's apply this styling. It gave indexes that we specified a designated color. This is a quick overview of analytics using Python. By now, you are better equipped with techniques to quickly understand and identify patterns within data. What will we be discussing next is, as we can see here, for example, we note an uptick in the Southeast region. Is this actually statistically significant deviation or change in the mean between each group or not? This is what we will answer next using statistical inferences to back up our exploratory data analysis. And lastly, we will finish off by applying a linear regression model to this data in order to capture the trends we have already identified and to be able to predict charges using a machine learning approach. So stay tuned and good luck.